These are the frequently asked questions for pre-calculus, and this is for section 2.6, day 3. In exercises 37 to 44, find the intercepts and asymptotes. Use limits to describe the behavior at the vertical asymptotes and analyze and draw the graph of the given rational function. Well, what I'm going to do here is kind of use the same template that we were using in class whenever we looked at these, and just go ahead and use this to analyze all of the behavior and talk through it as I go. The first thing we did in class was always to factor and see what we could see out of the numerator and the denominator. So in our denominator here we have 2x squared minus x minus 3. That's not a perfect square, trinomial, or anything like that. So what we would do is just good old-fashioned factoring, where we know that 2x times x is going to give us the 2, and then somehow we need to create a situation where we would get a negative 1 out of the middle term when the last two terms multiply to negative 3. So if that's going to happen, we would need a negative 3 here and a plus 1 on the outside, because first times first would give us 2x squared, outside times outside would give us 2x, inside times inside would give us negative 3x for a total of negative x, and then negative 3 times 1 would give us our negative 3 that we need in that last position. So now we have that information. As I mentioned before, I usually go after the asymptotes right away. So vertical asymptotes are where a denominator is going to equal 0. So we would want to know, when is 2x minus 3 going to equal 0? Well, at this point, most of us aren't probably going to write that down even. We're just going to put the vertical asymptote as x equals 3 halves. And then with that x plus 1, when does x plus 1 equals 0? Well, that's going to be when x equals negative 1. So these are important features, and usually if I'm losing track of things, I'll make boxes or circles or something like that if there's a lot going on. Then the next thing we would look at is the horizontal asymptote, and that has to do with, as we go to infinity, what's happening with this graph. And as I go to the original, I see there would not even be anything but the 2 on the top, and on the bottom, if we put infinity in here, that number for this polynomial down here is going to get bigger and bigger and bigger, so much so that we won't be able to tell the difference between that and 0. So our horizontal asymptote is going to be y equals 0. Now our x-intercepts, remember, come from something 0. That's what we're always trying to get with our x-intercepts. Well, the only way that happens is when our numerator is 0. We don't have any way to make the numerator 0 in this one. It's a 2. There's nothing we can do about that. There is no math magic wand that's going to make that disappear. So we don't get one. And that's what happens when there's just a number in the numerator. And then our y-intercept is always 0, and then whatever number we get. So we can go back to the original and see that this will be a 2, and this will be 0 and 0 minus 3. So that's going to be a negative 2/3. And get those pieces. And at this point is when we would at least get those asymptotes on our graph so that we can start to see the way the graph is shaping up. So we have that x equaling negative 1 and x equaling 1.5. And then we have a horizontal asymptote at y equals 0. We've got our two verticals on there. And then let's put the 2 points that normally we would have. In this case, we only get 1. We don't have an x-intercept, but we do know the graph is going to cross at 0, negative 2/3. Now what this does is it sets a situation up for us where we can see this really has been segmented into 6 different sections. And so an important part of this is going to be putting something in here so that we can see where is this graph going to go, and we can talk about the numbers. So the first place to start is usually the positives. That's where most people will go when they want to know what's going on with the graph. And again, we had 2 over 2x squared minus x minus 3, and I want that handy so we can talk through the math. Well, we're at 3 halves for that rightmost vertical asymptote, so maybe we should go ahead and try 2 and 3 so we can get a feel for that branch. The 2 on the top of this fraction is going to stay there. It's just a matter of putting our 2 and 3 in below. So 2 squared is 4, 2 times 4 is 8, 8 minus 2 is 6, and 6 minus 3 is 3, so that will give us 2/3. If we put a 3 into this, follow the order of operations, that will give us 2 times 9, which is 18. 18 minus 3 is 15, and 15 minus 3 is 12. That will be 2/12, which is 1/6. So it's getting closer and closer to the asymptote. And that really is enough, because we know what those asymptotes are for. We're going to get closer and closer to them without ever crossing. So now we have that branch in there. Then we would want to figure out what exactly is going on in between those 2 vertical asymptotes, which were at -1 and 3/2. And a nice easy number to throw in would, of course, be 0 to take a look at. Well, we already know that. We have that. That was one of our intercepts. So that's our -2/3. And we realize, okay, well, I need another number. I'd like to do something nice in there. Throw a 1 in. Why not? So if we put a 1 back in this original, we'll have 1 squared is 1, 2 times 1 is 2, 2 minus 1 is 1, and 1 minus 3 is -2. And 2 divided by -2 is -1. So 1, -1. Now what that does is it sets it up for me to see that because I know there aren't any x-intercepts for this graph, that branch must be going downward at this point. Now, if we're worried about that, we could always throw something in, like let's say -3/4, and see what we get. So that obviously is going to take a little bit more math as far as the squaring and everything, but you get an answer that would make sense. So I'm just going to quickly do that over here for you. 2 over 2 times -3/4 squared, that would be 9/16, minus a -3/4 minus 3. So here we could do a little bit of canceling and get 9/8, and minus a negative is going to make that a plus. And I'm going to go ahead and multiply the numerator and the denominator of that by 2 to get 6/8. And then we would have minus 24/8, which would give us the 3. So we have 9 plus 16, which is 15, and then we have 15 minus 24, which would give us a -9/8. So a -1 and a little bit. And that does set us up really nicely for knowing what the middle of that graph is going to do. And I took up too much space, so I'll erase this off of here. All right, next up, we need to know what's going on for the leftmost, and that would be to the left of x equals -1. Well, you should have a feeling right now that we're going to be up here. But if you don't know that at this point, then of course, you're going to make a little table, and you're going to use, let's say, -2 and -3, and see what we get, again, back in this original. I don't want to erase any of that so that you can see all those pieces up there. So if we put a -2 in, we'll have -2 squared is 4, 2 times 4 is 8, minus a -2 will be +2, so we'll get 8 plus 2 is 10, minus 3 is 7, and there's a 2 on top, so that would be 2/7. And then we could go ahead and put a -3 in here, and -3 squared would give us a 9, so 2 times 9 minus a -3 minus 3. 18 plus 3 is 21, and then you'd subtract 3 again and get 18, so 2/18, which is 1/9. And that just confirms what we already knew about this graph. We knew that this branch was going to be followed in fairly tightly into the corner, just like the other branch is. And there we are. So, limits. We are talking about a vertical asymptote at -1. So limit as x approaches -1 from the left, our graph, which did happen to be named f of x this time, as we approach that -1, our graph is going upward. Limit as x approaches -1 from the positive side of f of x. Well, as we come at it from the positive side, our graph is going downward. So -infinity. Then we need the limit as x approaches our 3/2 from the negative side. Well, our 3/2, as we approach from the left, is right here. And this would be going downward. So that is negative infinity. And then we have our limit as x approaches 3/2 from the positive side. Well, that's this portion of the graph, and that's definitely going upward. So that's going to be our positive infinity. All right, our domain. We have a couple of asymptotes that we need to jump over here. So our domain will be negative infinity to our -1, and then we jump over that and start up again and go to 3/2, and then we have to jump over that and start up again. Next up is the range, and we can see with this one that we're definitely going to have just a small chunk of y's that we are not using here. And that's that piece where we would have to go ahead and use the graphing calculator to figure out exactly where that point is. And that point ends up being at 1/4. And I know you guys can go ahead and find that little max on your own. I'm not going to bother doing that. -16/25. So we're coming in from negative infinity, below it, and we're going to get up to that -16/25, which is our y value. And in fact, this one is perfectly -16/25 because we are not rounding at that spot. And then we have to make a jump, and that jump is coming up to these two branches, which we know are going to approach 0, but they're never quite going to make it. And then that goes on to infinity, forever. Now, we talked about the fact that all these rational functions are going to be continuous. So it's continuous, but we have to say continuous where. And the where is we have to leave out any of those x values that are not going to work. So continuous for x not equal to -1 and 3/2. Those were our two vertical asymptotes. Increasing and decreasing, we've got a bunch of that going on. So first, I will go after decreasing. And then I go back up, and as I talked about in class, I mark anything that I can see that is going downward from left to right. So that is this portion of the graph right here, and this branch, and that's what I need to represent. So the first portion is starting with the x value of 0, and then it's continuing on to that 3/2. So the first decreasing portion that we have, and it wasn't perfectly 0, it was actually the 1/4 at that highest spot. And that's going to take us to our asymptote of 3/2. And again, the book does use closed brackets for that 1/4, but we talk about how something can't be increasing or decreasing at a point. So technically, we're going to tell you to do that with open brackets anyway. And the other portion of that was on the right-hand side of that vertical asymptote, which was 3/2 and off to infinity. Then we have increasing to go after next. So our increasing portions are going to be that leftmost branch. So that's going to be this piece is increasing, and this piece is increasing inside here. So we're talking about negative infinity up to our -1. And then for our little branch, we have our -1, our vertical asymptote there, and then that goes up to that 1/4, which again, we're going to go ahead and use open brackets for, and kind of disagree with the book on that case because it cannot be increasing or decreasing at that point. Symmetry, not this one. Bounded, no, going up and down forever. The local extrema? Yeah, absolutely. We found a local max of, and that was negative 16/25 at 1/4. So that was our local max that we had. And then the last thing is the end behavior. So the limit as x approaches negative infinity of our graph f of x equals, and the limit as x approaches positive infinity of f of x equals. And as we go to the left and the right on this graph, this is definitely approaching our horizontal asymptote, which is 0. So both of those would be 0. And I believe that takes care of everything for that graphing problem. Is the next one on your list here. And again, we'd start by factoring if at all possible. So let's take a peek at this and see if it's factorable. We do not have a perfect square trinomial. So we would be looking for two numbers that multiply to -3 and add to 2. And that would be +3 and -1 that would make that happen. Now, while I'm looking at that, I'm checking to see that nothing's going to cancel out because I always want to consider the fact that there might be some holes. And I notice that this will have a slant asymptote. How do I know that? Because the numerator, the degree of the numerator is greater than the degree of the denominator. So I'm going to start by finding that information, and that means making those first terms match. And since x works, we're going to change the sign here, and we'll get 0. And right away, we're down to our remainder. So with this one, we're going to have a slant asymptote. And it will be the line y equals x, which is that perfect diagonal through 1, 1, 2, 2, 3, 3, etc. All right, asymptotes. Well, vertical asymptote comes from the denominator equaling 0, so that's going to be x equals -2. Horizontal asymptote, well, if we have infinity squared over infinity, we're still going to have infinity if we cancel one of those out. So we don't get a horizontal asymptote. It does not have any. X-intercepts, well, that's where we make our y value 0. And the only way that's going to happen is if our numerator is 0. So those are our two zeros from up here, and that will be -3, 0, and 1, 0. Again, the x-intercepts always come from your numerator equaling 0. A 0 in the denominator is undefined, but we can have a 0 in the numerator. Y-intercepts come from 0 and then something. So we're going to go back to the original, and we're going to go ahead and put 0 in there and see what happens, and we would get -3/2 for that one. So we've got a lot of information already, and what we want to do is sketch what we have. So let's put on those the vertical asymptote at x equals -2. And we have that slant asymptote, 1, 1, 2, 2, 3, 3, 4, 4, -1, -1, -2, -2, etc. All right, now let's get our points on there. We had x-intercepts at -3, 0, and 1, 0. And we had a y-intercept at 0, -3/2. All right, so now what? Well, we use what we see, and the fact that the degree of the numerator was greater than the degree of the denominator, and we try to figure out what the graph will look like before we start putting points in. And as I talked about earlier, we can see from this, especially with that slant asymptote, that our graph is going to do something along these lines. But we would want to know exactly where that's going to be if this is a test question. If it's homework, I'd be really tempted to just go ahead and slide those in alongside those branches. But our 43 was x squared plus 2x minus 3 over x plus 2, which we factored into x plus 3 times x minus 1 over x plus 2. And quite frankly, I do have enough on the right-hand side of this to say, you know what, I've got 2 points. It's going to look like that. And that's what I know. But I might want maybe just one more point on the left-hand side if this is a test. So maybe I put -4 in and see what happens. -4 plus 3 is -1. -4 minus 1 is -5. And -4 plus 2 is -2. So we'll get 5 halves. So -4, -5 halves, of course. 1, 2, 3, 4, and 1, 2 and a half. Now that's enough. And that's because I know that those asymptotes are going to work. So now that we have that information, we can talk about the limits. And that would be, in this case, just that one vertical asymptote of x equals -2. So the limit as x approaches -2 from the left of, and this was not f of x, this was h of x. Again, you want to be careful with that so you don't get dinged for presentation error in calculus. And then -2 from the right. So as we approach our -2 from the left-hand side, our branch is going upward, infinity. As we approach -2 from the left-hand side, our branch is going downward, so -infinity. Now, our domain, well, we really only had one x value we couldn't use, and that was -2. So -infinity to -2, hop on over it, and start back up. Our range, well, these are going up and down forever, so that's going to be -infinity to infinity, all real numbers. Continuity, absolutely. It is continuous for all x not equal to our -2 vertical asymptote there. Increasing and decreasing. Well, let's take a peek here. As we draw this branch from left to right, we're going up. As we draw this branch from left to right, we are going up. So both of these pieces are going to be increasing. We just need to go ahead and put the intervals. So from -infinity to our -2, and then hop over that -2 and go on to infinity. And those are both going to be increasing. Symmetry, well, no. I mean, we'd like to think there is, but there isn't that even or odd symmetry that we're looking for. This is not bounded above and below. Local extrema, didn't get any of those. But of course we have end behavior. So the limit as x approaches -infinity of h of x, and the limit as x approaches positive infinity of h of x is what we're interested in. So as we go to the left forever with this graph, pretty obviously this thing is going to go down. I mean, it's gradual, of course. Let me go back up here to the picture to show you. But we're going to follow along that slant asymptote. So going down. And then as we go to the right forever, this is going up. So -infinity and infinity. And that covers everything that we needed to have for this problem. Problem up, you had asked about number 44. So with number 44, just like with the others, we're going to go ahead and factor anything that we can factor here. So our numerator appears to be factorable. It's not a perfect square, but to find two numbers that multiply to -2 and add to -1 would be -2 and +1. So we have those pieces there. And again, that factoring is what we want to see. Now one more time, I see that the degree of my numerator is greater than the degree of my denominator, which means that I'm going to be working with that polynomial long division to figure out my slant asymptote. So this one is going to need to be multiplied by x, and that will give me x squared minus 3x. And then I have to change the signs and add. So that will give me 2x minus 2. So my x minus 3 is going to need a 2. And I multiply that out and get 2x minus 6. Change the signs and add. But that part is the remainder, so I don't necessarily need that. This is my slant asymptote. and that is y equals x plus 2. All right, we keep going, and we use all the information that we have. So, vertical asymptote, that's where the denominator is going to equal 0, and that's going to be at x equals 3. Horizontal asymptote, well, when the degree of the numerator is greater than the degree of the denominator, and we put infinity in here, infinity squared over infinity, when you cancel out an infinity, it's still going to be infinity, so we don't get one. Then we go after our x-intercepts, and our x-intercepts are where the y will be 0. The only way that the y is going to be 0 is if the numerator is 0. That only happens if these two factored forms are 0. So that will give us 2 and a negative 1. The x-intercept is what happens when we put a 0 in, or sorry, y-intercept is what happens when we put a 0 in for x. It's always opposite. So 0 minus 0 minus 2 is negative 2. 0 minus 3 is negative 3. That's going to give us 2/3. So we have some points on here, and we also have some asymptotes that we know that we're not going to use. So vertical asymptote is at x equals 3. And we had a slant asymptote, which was at y equals x plus 2. So we want to get that on, and if it's y equals x plus 2, that's just y equals mx plus b. So we're going to go up to 2, and then we're going to go ahead and go up 1 and over 1, and that will give us our asymptote. Which is, of course, really important and will make getting our branches figured out much quicker. So now, we put on some points. We know that we are going to go through 2, 0, and negative 1, 0. And we know that our y-intercept is 0, 2/3. Right there. And so far, that's the information we have. 3 points and our asymptotes. So now, let me go ahead and rewrite that function. K of x equals x squared minus x minus 2 over x minus 3. To do would be to figure out where these branches are going to go. And pretty obvious branch down below here. Now, the question becomes, how far in does that go? And so what we would want to do is definitely take a look at what exactly is going on where x equals 1. So we can put that 1 back into either the original or the factored form and figure that out. 1 minus 2 is negative 1, 1 plus 1 is 2, and 1 minus 3 is negative 2. So the two negatives are going to cancel out, and we're going to end up with a nice little 1. So 1, 1. So we can see what that graph is going to be doing. And because we know this one had that slant asymptote, we get a good idea that the other portion of the graph is going to be where I just put that nice blue dot up here somewhere in this region. Well, that means we need some points in that region. We need to be able to see what's going on and how far that's going to go. So our vertical asymptote was at x equals 3. We might just take a look at 4 and see if that's enough, you know, if we know what's going on at 4, but we also might want to like throw 5 in just to be certain. So 4 minus 2 is 2, and 4 plus 1 is 5, and 4 minus 3 is 1. So that's at 10, right up here. And then because that ended up so high, again, I might want to go ahead and put in a 5 just to see what happens. 5 minus 2 is 3, 5 plus 1 is 6, and then 5 minus 3 is 2. So that would give us a 9. And now, because I know where those branches are going to go with that slant asymptote, I can go ahead and put that branch in. And of course, that makes this whole process of looking at those limits easier. So the limit as x approaches, and again, our asymptote was as 3, so 3 from the negative side, and this was k of x. And our limit as x approaches 3 from the positive side for k of x. So what we see here is our vertical asymptote right here at 3. And what our graph is doing as we get closer and closer to that is it's going down. That's kind of a goofy looking infinity. There we go. And as we approach from the right-hand side, our branch is going up. So we have those limits for what's going to happen at that 3. And now we're talking about domain. And we realize there was only the vertical asymptote to leave out. So negative infinity to 3, jump over 3, and go on to infinity. Our range, well, we have to take a look at that, and we do notice with our range that we absolutely have a jump with our range. So we have to figure out where these points are at. And what we would do with this is we would use the graphing calculator to figure out just how high are we talking about with the range. And just to save time here, the highest point that we had on this one, I've gotten a little carried away, that was at 1. So our y value here was at 1. So 1, 1. And the point that we found when we went through the table where we had a 9, that is actually the lowest points. That was 1, 2, 3, 4, 5, 9. For that lowest point. So that means we're coming up from bottom, we're using negative infinity to head upwards, but there's a cutoff at 1, and then as we go on the other side of this, and actually we can include 1, because it does, we did have a point, 1, 1 at that point. And then we can do the same thing with the 9 and go on to infinity for our range. And the next piece is our continuity, and we realize that again it's that vertical asymptote that we have to leave out, so it's continuous for all x not equal to 3. Increasing and decreasing. Well, go back to the picture and we take a peek and we see that this portion of the graph is decreasing and this portion of the graph is decreasing. So what we want to do is explain where those x values are at that are giving us that decreasing behavior. And that's why it was so important that we're able to figure out that local max and that local min and get those pieces. So we're decreasing from 1 to 3 and 3 to 5. And then what do we have? Oh, if you're wondering why it is that those two are cut off, remember that we have our vertical asymptote. So that's the piece that we have to give that decreasing for. And then our increasing is wherever our graph appears to be going upwards. And that's going to be from negative infinity to 1, because that's our first increasing piece. Let me choose a different color here. This is going up. And then here is our next increasing piece over here. So our increasing is from negative infinity to 1, and then from 5 to infinity. Symmetry. Nope, we don't have any even or odd here. Bounded. No, this is going up and down forever. And then we have our local max and local min. So a local max of And that point that I said we'd probably use a calculator to find there, that point was 1 at 1. And then a local min of, and the other point that we had to find, and that was 5, 9. It just ended up being perfect. So a local min of 9 at 5. And then finally our end behavior, the limit as x approaches negative infinity, and this one was called k of x, and the limit as x approaches positive infinity, and that again is of k of x. So if we go back and we look at the graph and we consider as we go to the left forever what's going down, let me bring that graph back here. As we go further and further to the left on our graph is going downward. As we go further and further to the right of our graph, we are going upward. So we're going to need negative infinity and then infinity. All right, so that summarizes everything we needed for number 44. Next up is 64, and number 64 is asking us whether or not f of x equals x squared minus x over x squared plus 4, if that's a rational function. In order to be a rational function, we must have a polynomial divided by a polynomial. And a reminder that we need to have those whole number exponents. So as I'm looking at this, the numerator is definitely a polynomial, but the square root of x squared plus 4, would there be a way for us to simplify that so we have whole number exponents? And that would mean taking x squared plus 4 to the 1/2 power. Now, we can't distribute that 1/2, so there's absolutely no way for us to simplify that. So our answer here would be no, because the square root of x squared plus 4 is not a polynomial. It is not a polynomial. 69 says work in groups of 2. Well, we didn't necessarily do that, but compare the functions. And f of x, of course, we notice is going to factor in x plus 3 and x minus 3 over x minus 3. And that tells us that this graph is going to have a hole at x equals 3. G of x is just x plus 3. So A says, are the domains equal? Well, for f of x, the domain is going to have that hole of 3. We can't use that. So negative infinity to 3, skip it, and go to the other side, 3 to infinity. But our domain for g of x, that's all reals. There isn't anything we can't add 3 to. So the answer to that is no, they're not the same. B says, does f have a vertical asymptote? Well, no, it's not an asymptote. No, it is a hole. It's a point of discontinuity. C says, explain why the graphs appear to be identical. Well, we could put, because the graphing calculator is stupid, but that wouldn't necessarily be the way we would want to word something as a justification on the AP Calc test. So, the grapher does not know to exclude x equals 3 from the domain. Graphing calculators are built to try to connect everything up unless you're in dot mode, so it's doing the best it can do. D says, are the functions identical? No, absolutely not. And that would be because f of x has a hole in the graph. So this is all about that point of discontinuity. And we had one or two of these in the notes as we went through that you have to be careful, including that example 9 that everybody should be watching. That's it for this FAQ.